So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Salvatore, Francesco, Emanuel, Oliviero, who will tell us about non-Clifford cost of random unitaries. Okay. Wait.
Hi to everyone.
Wait, I didn't have your introduction with me here. Sorry. Yeah. Postdoc at Quantum Information Theory at Scuola Normale Superiore di Pisa. He earned his PhD under Alyosha Hama at UMass Boston. His research covers quantum chaos and information scrambling, research theoretic approaches to magic and entanglement, quantum learning theory, and the role of quantum information. And he's also investigating quantum complexity that underpins the difference between classical and quantum states in information processing. Yeah, sorry about that. So Salvatore, the floor is yours.
Okay, so hi to everyone. So thanks for the invitation to give this seminar. It's really an honor for me. So as mentioned by Jello, today I'm going to talk about the non-Clifford cost of random unitaries. So the topic will be mostly on how Clifford plus non-Clifford behave with the random unitaries. So before to start, I will just give a brief introduction to the collaborator of this work. So this work has been in collaboration during my PhD with Lorenzo Leone, under the supervision of Alyosha Hamma. Now Lorenzo is an assistant professor in Salerno, while Alyosha is a professor in Naples. And then we had two additions to this project that are Jens Eisert, that is a full professor in FU Berlin, and Lennart Bitter, that is a postdoc here in Berlin. So the work is this one. I think that you know it since well. But anyway, so what is the outline of this presentation? I will start with some motivation of why do we care about why do we care about random unitaries, why they are important, why we should study them. And then I will present briefly my main results, because I don't know how much time it will require to give you the preliminaries, but in this way you have cleared the main results, and then we can eventually sketch up the proof after. Then I will give you some preliminaries on random unitaries and Clifford plus not Clifford. Maybe you have some knowledge about it, but it's good to have notation and stuff on what we do. Then some proof sketches, so the idea behind our proofs. And then I will present briefly the new results on the topic that have been made by Lorenzo and Lennart. It's a new work. I think it went under the radar, but it kind of improved what we did in this work. And then I will conclude my talk. So let's start with the motivation. So why do we care about random unitaries? Why they are important? So in general, also for classical application, we usually care about randomness. So it's useful for some algorithms. They improve the performance of some kind of algorithms, so it's good. Also in quantum, they are important in the sense that they are central for tasks like cryptography, to encode stuff, benchmarking, thermodynamics, but not only. For example, in tomography, they're also useful. And also they have application, for example, to model chaotic dynamics. So in a certain sense, study random unitaries is important because it gives us many applications, and it also allows us to understand better nature and stuff. But what is the main problem? So if you want to apply this kind of concept of random unitaries, in principle, exact sampling is infeasible because we have many unitaries. They have circuit complexity that is exponential. So sampling random unitaries, it's hard because we should be able to reproduce this kind of unitary. So what can we do? So how to implement this kind of random unitaries? The main idea will be to approximately, so there is this concept of approximate k-design that I will introduce better later. But the idea is that we have some distribution connected to this sampling process. And so the idea is to approximate some moments of this distribution. And so these are kind of the idea of the k-design. And we want to approximate it with some kind of error, because of course we will not be able to reproduce these k moments exactly. And the idea is then, okay, now we have Clifford, because we know that Clifford are a good group. We use it for fault-tolerant computation, many applications, and then we have to add this kind of non-Clifford gates. And the idea is, how can we approximate random unitaries in this concept, in the Clifford plus T architecture? Of course, when we build these kind of things, what we will kind of discover is that non-Clifford gates dominate the cost. in the sense that there already have been studies on this, and basically the cost of the non-Clifford gates exceed the one of the Cliffords. But so the question is, what is the minimum amount? So the topic will basically be on understanding what is the minimum amount of non-Clifford gates that we should use. And so what is the problem setup? So as mentioned, we will work in this Cliff plus T scenario. So we have our circuit ensemble that you can think of. We have some Clifford, and then we interleave them with these single-qubit gates, these single-qubit gates. In general, it can be whatever, in the sense that we don't care that it's, for example, the gate. It can be a random rotation. And also, it's not a real problem that, so we can have here, for example, also CCZ, because the difference will be just, one factor. So it's not really a problem. And basically we interleave and we have T of them, and we want to understand how big should be T to reproduce these K moments. And so the goal is to characterize the minimal non-Clifford count in order to reproduce additive and relative approximate K design. Of course, this notion here for now are kind of laid out. I didn't give you too much, but it's just to introduce the results. So, and of course, in this problem, we introduce a tolerance epsilon that we want to care about, because of course, the results will not be exact. So we not expect to reproduce exactly the K moment of the R distribution, but there will be an error. And on this comes this additive and relative notion of error. So that said, I will just lay out the first result. So we have first result on the frame potential. Why it's important? Because it will give us an important results on state design. So the main thing is that basically we can see that in this regime, where basically n is omega k squared plus T log k, the difference between the frame potential of the ensemble of this circuit ensemble minus the one of R is bounded between two functions that scale both quadratically in k squared. This tells us that if we want to converge to R, the minimum amount should be omega k squared in this regime. And why this is important? Because there is an important relationship between the distance between the state K design T and R, and this is bounded by the relative frame potential. I will introduce it better in a second moment. But this basically tells us that also state design converge in omega k squared. And this is important because this is really reduced what was known before, because this was k to the third. So this is a huge improvement on the literature. But then we can also obtain results on the relative unitary designs. So we want to approximate in relative error. And basically we have three different regimes. So when k is smaller than n over 2, basically we obtain that the number of T should scale with n times k. If k is instead square root of n, or square root of n, what we observe is that basically this should be omega tilde, where tilde is basically a logarithmic factor, and k, so we have this n times k all the time. But when we instead basically have that k is larger than n, this T is omega k, because now basically we restrict everything. What is important also to say is that for this region, we obtain an optimal scaling, in the sense we have matching upper and lower bounds. So this is an important result, because in this sense, we have something that is clear and well developed. So now on this, we basically have everything. Okay, and so let us start with some preliminaries. So we want to talk about unitary K design. So the first things to introduce is the K-fold channel. So in the sense that, as mentioned before, we want to understand the moments, and the best way to do it is through this K-fold channel. So the idea is that we just take an operator O in our Hilbert space, tensor O times tensor K, and basically we twirl it with the U tensor K. So this is in order to generate the K moment of this operator, and we study how does it behave. So what is interesting is that since U tensor K is a symmetric operator, this basically has a representation in the symmetric group. And so this can be expressed with this nice expression where T are basically permutation operator, while omega minus 1 are the Weingarten function. So to understand how this can be obtained is the following. So if we twirl some permutation operator, we can expect that it has to remain itself. And so basically we obtain that T sigma should be equal to T sigma, but this coefficient, this sum should be 1. And so basically we can obtain this Weingarten function as the inverse of the grand matrix given by the trace of T pi T sigma. So that's basically the main idea, and these really rely on representation theory. I will not go further on this, but this is kind of the decomposition that we have to be in mind in terms of what happens when we twirl an operator. And what is important is that, of course, this kind of function can be approximated when D is large, and they have this nice scaling in which the dominant part is given by the diagonal. So because we have this 1 over D to the k scaling, while the off-diagonal term scales with a term that is at least d to the minus k plus 1. This because when pi is different from sigma, the distance is at least 1. That's basically. And this is important because we will see that with Clifford we have a similar behavior, and this will be of use in our proofs. So this is something that we should always keep in mind. But now, how do we define a unitary K design? So now we are not considering the whole set of unitary operators. Now let's say that we have a smaller set of unitary operators, and to each unitary operator we tend to assign some kind of probability. So in the sense that when I sample, there is a certain probability that I get a certain unitary or another one. And in this sense, we say that this is a K design if the k-fold of over this ensemble is equal to the 1 over R. And of course, since now we are considering a discrete distribution, in this sense, the k-fold will just be given by the sum, the weighted sum of this tensorfold of the operator, of this twirling of this operator. That's it. It's nothing too important. And what is interesting is that we can connect this notion also to the frame potential. I introduced before the notion of frame potential, and I told you that was important in order to obtain some results on state design. Why that? Because basically, so the frame potential can be seen as an averaged overlap between unitary of the same ensemble. And what is interesting is that, so if we compute the frame potential for a certain ensemble, this is always greater or equal than the 1 over R. And 1 over R should be k factorial because the permutation are k factorial, and since this is kind of connecting to the overlap and the sides of the set, this one should be k factorial. And we say that we have an exact k design if the frame potential over the ensemble is equal to the frame potential of R. So if we have, for example, a way to access the frame potential, we also know, and we know that it's equal to the frame potential of R, we basically can say that it's an exact K design. But unfortunately, unitary K design with K greater or equal than 3 are not so easy to implement. What I mean is that basically the only known K equal 3 design is the Clifford group, and it only holds for qubits. If we instead go to qubits, there are only 2 designs. And we don't know any other sets that basically can achieve the 4 design, and probably there is no other one, probably because we lose this kind of group structure that we have first with Pauli, then with the Clifford group, and then we have really the unitary group as the things after that. So in that sense, we don't have unitary K design, so we need something that, so as usual, we are not desperate in the sense that we are not trying to reproduce things exactly. We can introduce some notion of error. So in general, there are 3 definitions of error. I will just give you the first 2 because the third one has been introduced later, and it will be relevant for the things that I will say about the work of Lorenzo and Leonard. And basically we have the first one, the additive error K design, where basically we just look to the difference between the channel given by the K-fold over the ensemble and the R channel, the R12 channel. And what we want is that basically their distance in the diamond norm is smaller than epsilon. This is basically telling us is that if we have some quantum algorithms that query U tensor K, and we are applying it on a state, then basically the distance between what happens on the ensemble and the R measure, its in trace distance is smaller than epsilon. So that's basically it. In general, it's basically computing the worst case scenario if we are using some kind of quantum algorithm. This is strong, but what it cannot do is basically to consider adaptivity. And so for this reason, people introduce the notion of relative error. This is a really strong notion because, of course, this is really bounding the eigenvalues each eigenvalues of the channels. And what we require is that the k channel of over the ensemble is smaller than one plus epsilon of the channel of R and greater than 1 minus epsilon of the channel of R. This is a really stronger notion of closeness. It implies, of course, the adaptivity, but it's really an hard requirement in the sense that we will require a bit less and still obtain adaptivity. And I will show you later this kind of notion that also takes into account adaptivity. And of course, we can expect that there is a connection between additive error k-design and relative error k-design. And this notion is basically given by the fact that, of course, additive error is less strong. So if we have a k-design in additive error, this implies that there is d to the k epsilon approximate k-design in relative error. So we can see that if we have additive error, we have a relative error design, but it's really bad, the scaling with the dimension, because it will scale with t to the k. And so we require really an exponential precision in order to obtain some relative error that is useful, even in O1. Conversely, if we have a k-design in relative error, this is a 2 epsilon approximate k-design in additive error. And this can be shown with some telescope proof. So this is kind of the idea. And we know now that there is this kind of connection, and then we will examine also how this behaves. But then we can also, so I mentioned some results on projective design. So we focused on unitaries, so on this unitary twirling. What happens when we consider some set of states? So of course, we can take an ensemble, assign to each state some probability. So this will give us some measure. Now, I will give you in the continuous form, but it can be discrete basically as we used for unitaries. It's basically the same. And then we say that this set is a projective design if this channel is this operator is equivalent to the one of R, where the one of R is basically the twirling, the k-fold twirling applied to a state tensor K, where of course this is pure. And this is important because of course, while we could care about the behavior of unitaries, we can also care about the behavior of states. But of course, there is always the same problem. So we want something that is exact, but it cannot be reproduced. So we cannot have this exact projective k-design, but we can have something that is approximate. So something that it's really close and can be approximated. And in this sense, the definition is basically the same. The only thing that changes is that while before we were considering diamond norm, now we were considering the one norm. And there is a nice relationship in which basically the one norm distance between the ensemble k-fold operator and the ensemble k-fold operator for R in norm 1 has to be smaller than the square root of the relative frame potential. Thing that I forgot to mention is that, so now here you see the purity. Why is it called the relative frame potential? So basically what one can show is that the frame potential for state design, so where basically you consider the average overlap between states, can be basically rewritten as the purity of the k-fold channel. This is basically it. And so while here we'll have the purity of the ensemble minus the purity of the R divided by that, then we obtain this kind of formula. And this is really useful because make computation like a lot easier and helps a lot in computing the frame potential, the fact that we have this nice expression. So that's basically it. And I think that, okay. So are there any questions about this point until now, or I can move, in this way, it will be easier to move on. Okay.
I think there's no question.
Okay.
For now.
Cool.
Yes.
Okay. Just to... Okay, so now this will be quick because I think that everyone knows about polyoperator and Clifford group, but it's useful to set up some notation. So we can consider for single qubit the polyoperators, so given by identity X, Y, and Z, so written in terms of the polymatrices. And we build the polygroup as basically some phases times the TensorFlow product of P1, Pn, where these are single qubit polyoperators. And the phases can be plus minus 1, plus minus I, and they form a group that is 4 to the n plus 1 under multiplication. So what is interesting is that the Clifford group, why is important, is because basically it's the normalizer of the polygroup. That means that when it acts on a polyoperator, it returns a polyoperator. And what is interesting is that it's classically simulable. It can be generated by three smaller gates: Hadamard, phase gate, and CNOT. And to generate all the stabilizer states, one can basically act with the Clifford operators over C over the zero state. That's basically the basic introduction of polyoperator and Clifford group. So we can move on the idea of, okay, now we have this group. This is a set of ensemble. Now we can think, okay, now we can build our ensemble with a uniform probability distribution and each element of the Clifford group. So now we have our ensemble. So basically, this is kind of the definition of the twirl for the ensemble, because now we have the uniform distribution, because of course they have all equal probability, and then we are twirling this operator. I forgot the times k, I'm sorry. But you can expect, okay, this is just for one, but you can expect that for k, this is c o times k, and so forth and so on. So why it's interesting, the Clifford group? So as mentioned before, for qubits, they form a tree design. And the thing that I would like to mention is that if we consider stabilizer states, they also form an approximate for design. This is known, and it's a really nice result. And what is interesting is this thing. So moments can be written as function of polynomials. What does it mean? So as I mentioned before, Clifford does these nice things of taking polyoperator and mapping them to polyoperator. So we can kind of expect that the commutant can be expressed in terms of function of polyoperators. So of course, now said in this way, everything can be written in terms of polyoperator because of course they are a basis, but as O times power of P, in the sense that C tensor K will be mapped in objects that are P tensor K. So I will give you the polynomial in this way, which will be easier. So basically, this is the form of the polynomials. Now, I don't want you to be scared by this weird formula. It's less complicated than it appears. So we take some polyoperators. Now we have basically our K moments. And we can think that, of course, we can have smaller K moments in the sense that, of course, we don't need them to be the full K, but they can be smaller. So basically, we can have this matrix that encodes the column of the products of all these polyoperators. And what is interesting, in order to be in the commutant, they have to be in a way that the weight of these columns should be even. Why that? Because if we have, so for example, so I mentioned before that you are again in the polygroup, but what happens when basically you twirl something that is, so if for example you do C O C dagger, what you can get is a phase. So, but if instead you use even, so you have C tensor 2, P tensor 2, C dag, then basically this phase doesn't exist anymore. And so basically you have an object that is really in the commutant. I hope that these things about the event, it's really laid out, but it's not so difficult to understand. And then you have this object. So now this is basically something that takes two polyoperator and tells me if they commutes, it's one. If they anti-commutes, it's -1. And this Mij is basically a matrix that encodes this kind of information. It's really a correlation matrix between Pi and Pj. It's written in terms of their anti-commutation relation. And well, that's kind of it. This is this form. What is interesting is that if you perform the twirling, everything can be written in terms of this omega. So this is really similar to what we have seen before for R, where now instead of the permutations, we have this omega. Other things that I want to understand, want you to highlight is that permutations are inside this omega, just because permutation can be written as basically 1 over the sum of P tensor P. So they are already inside these objects. They are in the commutant. And what is interesting is that this calligraphic V is a generalization of the Weingarten function. But here, instead of having the Weingarten function written as instead of having the trace of t pi t sigma, now we have basically that is inverse of the Gram-Schmidt matrix given by trace omega dagger omega prime. That's basically it. So we have really this kind of equivalence. We can do also a similar things for stabilizer states. So we can twirl the stabilizers and basically we obtain this nice formula where basically now we have the sum over all the possible monomial. And this will be kind of help for the future proof to have it in mind. Yeah, I think it's basically. And then, as I mentioned before, we can also have some kind of asymptotic behavior for the Clifford-Weingarten function. So now, few of them do not depend on this condition. So even if it's I say that n should be greater than this value, this function is always symmetric. So it doesn't depend on this constraint. This is also always true because this depends really on this coefficient. So it's really on how omega dagger, omega prime, so their Hilbert-Schmidt overlap. The diagonal term is always d to the k. Where we need this kind of information, it's all related in their asymptotic behavior. So from here on, we will need this kind of things. So first of all, we can bound the eigenvalues of this Clifford-Weingarten function between d to the k, and this p is basically the sides of the commutant. So I will call with this mathcal p the sides of the commutant. This is something that we should have in mind. And usually this scales like 2 to the k square over 2, 2 to the k square, yeah, plus some coefficient, but it's not so relevant. This is why we also have this kind of k square. D to the k minus 1. With this value, we can obtain a bound on determinant of this calligraphic V that is basically written in terms of the determinant of the diagonal. And with this kind of information, then we can bound each single element. So the diagonal term is really close to 1 over t to the k, that it's really similar to what we had for the Weingarten function. And this is basically the distance between 1 over d to the k and this coefficient. While if we take the inverse of omega, omega prime, this is 0. So it's 1 order smaller than 1 over d to the k with this kind of bound. And so in order to satisfy this condition, we need to fix these things in order that this is the game. Because of course, if it's smaller than a number that is greater than 1, it's not so useful. And these are really useful in the sense that really helps you a lot doing computation. I want to stress out this because, so a thing that I didn't mention before is that, of course, with permutation, we know that they are k factorial. So they are already a lot for 6 because we have 720 permutation to take into account. But with the Clifford group, the number is way larger. So for example, for 8, that it should be 40,000, for example, for the symmetric group. You have 1 million of elements to take into account when you want to do this kind of averages. So knowing the asymptotic behavior is really useful because one can then reduce to the dominant terms, so the one that matters the most, and just focus on them. This is really useful to obtain some asymptotic behavior. Of course, it's not the exact computation, but it really helps a lot to remove the elements that will just give us some subleading terms. And when this commutant is large, I think it's really useful. So it's really good to know, I would say. But now we move on non-Clifford gates. So how they enter this kind of picture. So of course, we know that non-Clifford gates are useful because they basically introduce something that makes more quantum Clifford in the sense that they introduce this notion of magic. And this is useful both in order to perform fault-tolerant computation and also in order to basically do any kind of computation that is useful and is not classical simulable. So I will reintroduce this concept of t-doped-Clifford circuit in the sense that, of course, as mentioned before, we can have some Clifford, then some t, then some big Clifford, another t, and so far and so on. And I will like to stress out again that this thing can be a 1. So of course the results could also be retrieved if t is basically scaled with something that is on the dimension, but it will really change the order of the scaling. And I think that it's really relevant because, of course, when we insert these non-Clifford gates in our circuits, we expect to be able to produce big Clifford gates, big Clifford circuits, but we expect to inject just a small number and with a small locality of non-Clifford gates. So that's kind of the thing. And then again, we want to find the K that basically approximate R. That's kind of the thing. And
sorry, can I ask a
yeah,
simple question here?
sure.
So when you like alternate between the Cliffords and the T gates, so there's always just one T gate in between. I guess there's no advantage in having parallel ones.
So when we produce the computation, yes, that's kind of the idea. But as was mentioned, the idea is that you can pile them up. So in the sense that you can have Clifford, you can have an even 2, 3, 4, 6 gate, and then another Clifford. It's not really a problem as long, so
At
in
least it
terms
doesn't
of,
affect the counting, right? I guess is the important.
exactly, it doesn't affect the counting because as long this number is of 1, so it doesn't scale with the size of the system, it will not really matter in terms of convergences. So you will not converge faster or later to the thing.
Okay.
That's kind of the idea. But then there is another thing of why we do that. It's because, of course, the Clifford circuit are spreading around the T-gate around. We need that the Clifford have this kind of, I will not say global structure because there is a newer results, I will mention it at the end of my presentation, by a group in Caltech, where they improve these things, but you need that Clifford is at least set to design. So you need some Clifford and you have this T, then Clifford, so they can be shallower. In this sense, you can take into account, they can be shallow. So you can take into account the fact that now you can have, in principle, more T, but you need to kind of build it in this way. That's, I hope it's clear what I meant, and if not, okay.
Okay, thanks.
So, of course, now we have this ensemble. We need to know how to measure. So how to perform the measure over this ensemble. So the main idea, I will go back just to have the picture, is that now we can think of Clifford, then T, then another Clifford. So the idea will be, okay, we can average over this Clifford, then we use an average over this single qubit gate distribution. It can be even one single T, and then we add and perform the computation. But since we have the power, we can also average on some kind of distribution over this single qubit gate. Then we average over the Clifford group, then single average, and so far and so on. This is kind of the idea. So we are piling up these kind of R averages with these different distributions, and then we want to understand what happens. So of course we know how to do the average over the single elements, but we don't know how they pile up. And what is nice, I think, is that basically the average will be kind of the same of what we had before. So we have these coefficients that depend on these omega things, but now there is a T dependence. And of course, we can expect that we have to converge to R. Now I will explain better why we have to do, but it's already clear that since we know that Clifford plus non-Clifford gates, it's universal. If we are doping, in principle, we should converge asymptotically to R, because otherwise that will mean that basically Clifford plus non-Clifford is not universal as we thought. So this is really a simple argument to understand why the only things that matter is that when t goes to infinity, this should basically be R. And what is interesting is that now the coefficients have some kind of Weingarten function that it's not anymore a Weingarten function, but it's a combined thing between the Clifford Weingarten one, this T that basically encodes the single qubit information. And of course, since we are repeating Clifford T, Clifford T, Clifford T, they will be repeated T times. And then we have the final average that basically is at the end. And then, of course, we have the trace of our operator. So that's basically it. It's really similar. So if one basically have the idea of our behave, has already an idea of how Clifford behaves, and then basically can kind of write in the same fashion the T-twirling operator without knowing anything. So this is kind of interesting how this structure is preserved even if we are basically doing different kind of operation. So of course, as I mentioned, we have to converge to R. And so for this reason, we can introduce this mathcal L operator. So this is basically defined in this way. So when omega belongs to the symmetric group, it has this form, and it's zero otherwise. So basically, this is only taking the symmetric information part into account. And then we define this delta as the difference between this operator and basically the symmetric part. And what one can show is that this thing, so this k-fold operator can be written in this shape. So as R plus this coefficient, where delta is to the t. And what we want to expect is that basically this correction term, when t goes to infinity, has to go down and go to zero. And so in this way, we should have this convergence. And this is basically the object that we should care about when we talk about convergence, because this is basically the one that is responsible for our random unitaries, our ensembles to go to R. Okay, so now, of course, we need to understand a bit better how Tikal and V-1 Tikal are made, just to understand better what happens next. So what are the properties? Of course, tau is Hermitian. It's not, it's Hermitian because, of course, we can measure and basically we can have everything there. I didn't mention what is K. So basically, as I said before, we can introduce some sort of distribution on the single qubit gate. And so we can average omega over this single qubit application. What is a nice thing about this omega that I didn't mention just because I didn't know how much time and I didn't want to bother too much. I didn't want to focus too much on the Clifford commutant, is that these omega are factorizable in the sense that they can be written as smaller omega that have the same shape, but tensor n. And this is really nice. It's really useful when we think about these kind of applications, because of course, it really reduces the computational thing, because we can trace out a full part, and then just have this single qubit omega. So this is useful because then when we compute the diagonal term, you can see we have this d to the k, that it's really similar to what happened to the omega part, but now we have this coefficient. So we have this coefficient that is basically this small omega, so the one for single qubit, times basically the average of the single qubit omega divided by 2 to the k. Now, of course, we can always think, just to give you some idea, of course, if this distribution was, for example, over single qubit Clifford gate, this will basically return 2 to the k and cancel these things, and in this way we'll obtain again the Clifford group, just to give you some kind of intuition how it works. And of course, since we know that basically these terms should have off-diagonal term that is subleading, this term is basically upper bound by 2 to the 2 times d to the k minus 1. Okay, so now we can look to what happens when we make the product of the Clifford Weingarten function to the minus 1 times this Tikal. And so as before, since we are focusing on the asymptotics, we need to restore the condition that I mentioned you before that depends on the size of the commutant and similar stuff, and to this kind of fight between D and the size of the Clifford commutant. And we can focus on delta because, of course, it's better than this one. It's the one thing that we will care. So, of course, this, for how it is defined, it's always zero when we look to the symmetric group by definition, because, of course, it's defined in this way. This is zero, and so this will cancel out exactly what happens here. But when omega does not belong to Sk, so basically, but what we have is basically this distance. So this is the diagonal term, that is the one that basically comes from here. And this is still bounded by this kind of function of the sides of the commutant divided by d. And when, of course, the off-diagonal term, and then we care that the off-diagonal term are not far from 0, and this is the bound that we have. So these are all the elements that we have that basically allows us to then obtain our results on the convergence. And what are the conditions? So the condition here, that's kind of the main point. Okay, so now we can look to the asymptotic behavior because of course this is delta, but now what we are looking are delta to the t. So we want to understand how big should be t in order to converge to the order k. That's kind of the point. So we can basically pile up a bit of algebra and basically study the distance between this and the object that we built. So of course, for the off-diagonal term, you should have something that is bounded by the operator norm. And so we obtain this kind of object. It's really algebra in the sense that we really have to pile up stuff. It's not so complicated. It's just really studying the distance and making bound. It's not so involved. So there are not so many things to think about. And then here we want the diagonal to be close to delta omega omega times t. So in this way, we reobtain that object that it's nice and we can produce computation about. So basically we obtain all the distances and that's kind of it. And what is interesting is that from here we can already observe that the convergence just depends on delta. So if the operator norm of delta is smaller than 1, then we basically converge to the twirling. And why I mentioned that this should be smaller than 1, because if instead we are looking, for example, for Clifford, so exactly Clifford, this is exactly 1, and so we will never converge to R. That's kind to give you still kind of an idea. And of course, the set can be, so it should not hold for any set that is set to design, because this will be reabsorbed in Clifford, and so we will always be stuck in the Clifford group. That's kind of the idea. They should not have any element that is outside the Clifford group, because of course you can have some kind of weird to design that, but that has some element outside, and then so. Okay, and so basically we have that everything is exponentially suppressed, and this scaling is basically the operator norm times t, and that's it. So now we can focus on our results. So now I mentioned the first things was the optimal frame potential convergence. So we want to study the convergence of the frame potential because this will give us results on projective design, like a state design. So we want to obtain these tight convergence bounds for the frame potential. So the first thing that you want to do is to, of course, express everything in terms of delta. I mentioned before that everything was written in this way. So the idea would be to like express everything. So the frame potential, the difference between the frame potential in terms of this delta. Then study this quantity, so express everything in terms of this quantity. And then basically I will show you that all these things depends on the convergence rates of this spectral form factor, this trace U over 2K. These are also important when we look to chaotic behavior usually. So we study for certain kind of ensemble, but this can be also used for study other non-ensemble. These are really non-functional. So the main technical ingredient will be first to lower bound this coefficient, so understand basically how it connects to the spectral form factor, and then bound the spectral form factor as a function of averages over single qubit distribution. So how do we proceed? So first of all, we have to bound this object. So this can basically, the computation can be carried out by using what we discovered before, so how it behaves. So the trace of, so I will go back in this way. It will be easier. So we will go back to object of these kinds. But now since we are averaging and we are computing everything exactly, we basically obtain this object, where basically this is the spectral form factor that I was mentioning before. And this is really the object that is giving us the convergence. So without this, we will basically, if this was 1 or stuff, we will be stuck. Well, not 1. If it was worth 2 to the k, we will be stuck and we will never get out of the Clifford group. So we can compute it for example, the diagonal ensemble. So we are considering the set of single diagonal qubits. Yeah, the ensemble of single diagonal gates, sorry. and they are ensemble. So where on qubits we can have any kind of objects. So they basically scale in this way. We don't care too much. This is a really it scales like 1 over square root of k and 1 over square root k plus 1. It's not really important in the sense that when but this is the object that somehow give us the convergence, because of course now we have this k scaling. And for diagonal unitaries, then we can observe that this object scales basically like square root of k to the t. And so meaning that if we want to converge to doped-Clifford circuit just by looking to this object, we need t to be k square. So we need k square non-single diagonal Clifford gates to reach this kind of behavior. So at this point, we have our theorem. So if basically we have this condition on k and t, so if we have this condition on n, where n should be greater than this horrible function of k and t, but this is always connected to what I mentioned about the sides of the Clifford commutant, and in order to take everything bounded in a way that it's always smaller than 1. That's kind of the point. So in this condition, we basically can bound the difference between the frame potential, and we can see that these two objects are basically scaling both as k squared. So basically, the convergence of this is really in k squared. And how do we obtain the proof? So the first thing is to notice that this object, so this difference can be written in terms of sum of omega of delta t omega omega. So of course, this is not the object that we discussed here, because it's not the power of the elements of the matrix, but it's the element of the matrix of the power, the sum over the elements of the power. But then we can use our Clifford Weingarten expansions. So now we can reconnect to this diagonal term of delta times t, plus some coefficients that we should bound, but then it's fine. Then we can use our lower bounds on delta omega omega, and then translate everything in convergence in t. And so basically we are able to obtain these results. The upper bound is really similar. It's really using this kind of notion as asymptotics. And then the corollary is the things that basically we can apply these results on approximate design, because as I mentioned before, there is a connection between the ratio of, so the relative frame potential. So when we are taking this and divided by R, but then the scaling should be the same. So the convergence of the relative frame potential to 1 should be the same. And so basically this is telling us that if we want to obtain an epsilon approximate state K design, we need at least K square non-Clifford diagonal gates. That's it. So this is our results on frame potential. Now we can focus on relative epsilon approximate unitary K design. So now here, what is the trick? So the trick is, since we have to produce a lower bound, we can consider a specific state case. In our case, we can focus on sigma tensor k. So this is one term, and basically we can show that this lower bound, the measure that I gave you. And then we want to understand how basically behave the largest eigenvalues of this object. So what can be shown is that, so we can basically decompose the channel, as I shown you before, so in terms of the omega function. And then we can basically pick, that's the reason of why I mentioned the importance of Clifford Weingarten function, the one with the leading order one. So what we found is that basically is the one with the omega infinity that is d to the k over 2. So we can use it. We can reduce basically that sum over all possible terms to just 1 omega, because this will produce a lower bound on this value. And then basically what happens is that if we compute, we will then obtain some object that depends on this unitary operator on which we are averaging, -1, and we have to contract this distance. And then what happens is that we are averaging, but we can choose to look to a smaller ball. And so we obtain basically this bound. It's really contrived. I don't want to give you, but the main intuition is that we really use the Clifford Weingarten, and then we basically do algebra, and then just try to find bounds in order to lower bound these eigenvalues. That's kind of it. But why it's important? Because then how the proof behave. So since we are doing this over the state, since we want a lower bound, we can look to this object. Of course, we know that phi kr, it's always the same because then we will end up in the symmetric projector. So no matter what, for A, all the eigenvalues will be the same. They will always have the same value because it's a flat projector. But then here instead we'll have different values. But in order to study the convergence, we just look to the biggest one, to the smallest one of this difference, because since we want positivity, what it has told is that the smallest eigenvalue is greater than 0. Are there questions? So we have that basically this, the smallest eigenvalues has to be greater than 0. And so since we know the highest eigenvalue, we can basically bound these things. And basically what we obtain is this convergence. So where basically we obtain that factor that I mentioned you before. And now we have this scaling in n times k. So what I want to mention is that as I will show with the results of Lennart and Lorenzo, this behavior, unfortunately, is due to our choice of the relative epsilon approximate. When I mentioned that it's really a stronger notion, that's what I mean. So since we have this notion, there is no way in which we cannot have this size dependence. This is really something that is unfortunately due to this choice of metric. In the sense that if we, for example, would have chosen something that is slightly less strong, then we could kind of lose this kind of dependence. And I will show you in a second. So this is for the lower bound, of course. So we have this scaling for the lower bound. Then for the upper bound, there are the results by Jonas Afferkamp in random quantum circuit or approximate unitary design, where basically he used this kind of technique of averaging over this distribution, and it's able to obtain an upper bound. And what is interesting is that if we are in this regime, so O of the square root of n, we have a perfect matching scaling, because from here we can obtain again the scaling that is nk, and of course it's a tilde scaling, because here we have this logarithmic dependence. But apart from that, they are really the same. And we can, of course, push our results to other regimes, specifically because we have the Clifford commutant for any k. So we can also look for when k is basically omega n. And when we are in that regime, basically t should be n squared. And this is something that we could expect because, of course, here we have nk. Even if it scales like k squared, that's what we would love to have, this should be n squared. So this is really compatible with what we had before. So in general, that we need k square objects in order to reproduce the k behavior when k is equal to omega n. So those are basically our main results. But then one can also think to apply them to, for example, pseudo-random unitaries. I don't know if you have this notion, but basically with pseudo-random unitaries, the idea is that there is no polynomial algorithm that can distinguish a pseudo-random unitary from a random one. And there are some results on that. So about the upper bound, one can use the shallow circuit construction because it's a specific use case. This has been developed by Schuster, Afferkamp, and Wang in random unitaries in extremely low depth. And basically this implies that basically the number of non-Clifford gates that one should use is order n polylog log n. This is really basic. While instead, for the lower bound, we use this kind of argument. So the main idea is a stabilizer argument that can be found in this efficient learning of quantum states prepared with few non-Clifford gates by Grewal, Iyer, Kretschmer, and Liang, where basically we have that the dimension of the stabilizer group of a state is basically n minus 2t, where t are the non-Clifford gates. So in general, this is kind of the thing for non-Clifford gates. Then non-random states are far from any states with dimension that is n minus k, where k is the moment that we are carrying out. And so in order for a polynomial time distinguisher to succeed, it's basically that t is different from omega n. And so from that, we have that basically t should be between omega n and this n polylog log n, non-Clifford gates of the number of t that we need to build these pseudo-random unitaries in order that they are really not distinguishable by random unitaries. Okay, so that's it for the non-Clifford part. So now we'll introduce the results of Leonard and Lorenzo that I think are really useful and are really new. So this is this paper, Adaptive Quantum Homeopathy. Unfortunately, I think that the choice of this title was not good enough to show the importance of the results. Because so what Lorenzo and Leonard thought was that basically the definition of relative K-design was too strong. While it's useful because it bounds all the adaptive protocol, it's not useful in the sense that sometimes gives bound that are too strong to be really satisfied by what we see. And basically they define this notion of adaptive norm in the sense that, as you can see by the definition, they are basically considering any adaptive protocol in which we change this V and we are considering the worst case scenario. And what is interesting is that with this notion of norm, so with this norm here, basically they use this idea. So you can have a big random Clifford, then a K-design, but on K qubit. So this is really important. I want to stress out that here are just K qubits, then another random Clifford. So you twirl basically this K-design. And the idea is that you obtain an epsilon-approximate K-design on n qubits. So this is a really strong result in the sense that basically now we are reducing this requirement that basically we have a size-dependent approximate design. So in the sense that we need a doping that scales with n, because here, if this idea is true, we have a scaling that is at most k for reason on. And instead we can dope it using, we can push the K-design through these random Cliffords somehow. And thanks to this idea, so they are able to show that with that kind of norm, basically one obtained that the scaling is K square. That it's basically the things that we would have expected to hold for any kind of object. And I think this is really useful in the sense that, of course, now all the behavior that we had before, the one that I've shown you here, basically here will be K square, here will be K square, and it will be still fine because it's omega n and it's square root of n. That's kind of it. I think this is a really nice result. I really suggest you to look to this kind of results. I don't want to talk too much because, of course, it's another work. There are a lot of techniques involved. But the main takeaway is that basically with a small seed, a small non-Clifford seed, one is able to basically build a higher K order just by having them on a small subset. And this is also really, yeah, I think it's really important in the sense that it's really pushing a lot in this sense. So this was basically my talk. So in conclusion, we've shown that the quadratic doping in K is necessary if we use diagonal K terms. And then in order to have full adaptive indistinguishability, we need the linear scaling in n and k. This only if we require relative error design. If instead we use this new notion of quantum secure design, we can drop this linear scaling and just have the quadratic doping. And this also shown basically the role of non-Clifford. What are the open direction? So now, as I show you, we have this ON, but we still don't know what happens when omega is the square root of n. This is still unknown. Then the idea will be to consider alternative idea of doping. So in the sense that, of course, we consider unitaries, but in a previous work by Lorenzo and I, we also consider, for example, the role of measurements, but we didn't accept that analysis here. So it will be interesting to understand what happens when we consider circuits, also because, of course, now things become more complicated, especially if we consider unitaries. One can approximate possible results for the state design case, because one can always use this kind of post-selection things. But for circuits, it becomes cumbersome to produce anything, and then introduce other metrics and understand if there are other notions to consider. Other works that I want to mention is this work that is designed from magic augmented Clifford circuits. This is a work by Zambi, Jai, Gu, and Bao. I mentioned from you that it's a work from a Caltech group. I think they obtain results that are similar to us, even if I have to admit that they do smarter things, in the sense that I will go back because it will be, well, probably let's use this one. So now imagine that our idea of Clifford T, Clifford, and so far. So now in our idea is that this random Clifford have to be global, in the sense that you have a real Clifford. The main idea of this work that I think it's really nice, and I think it's really a smart way of reducing the resources when we want to build these approximate random unitaries. It's basically to consider the fact that we don't really need the big Clifford. We need something that approximate this random Clifford. And what they are able to show is that there is a gluing lemma. So you can combine more shallower Clifford circuits on different qubits and still produce something that is close to this object. I think it's really a nice result because this really reduces the number of gates that we have to use and the depth of the circuit that we have to consider to build a random circuit. Because why in our case, it has to scale at least with the number of Clifford gates that one have. There you can reduce everything to a logarithmic scaling. So I think it's really nice work to keep in mind. And that's it. This concludes my presentation.
All right. Yeah, thank you very much for very nice and interesting results presented here. I think we're kind of like at the time limit of the seminar, so maybe I'll allow like a quick question from the audience. Sure. Okay, I don't see anyone, but I did want to ask something. So, yeah, I mean, I guess like there's a lot of technical details, but I imagine, so you were doing this for Haar measure on unitaries, but you can do some calculation also for, I think that they sometimes consider like symplectics or the orthogonal group, and some similar results can be obtained, I guess, in that case.
Yeah, I would say, so for the symplectic, yeah, so for sure you can kind of consider other groups in the sense that, of course, we are considering kind of a set of gates in the sense that we are choosing the Clifford group and we are doping it with the non-Clifford group, the element outside of the non-Clifford group. What can be done is basically consider any kind of, for example, the real Clifford group, because there the commutant is different. And then you can still use the doping with the T-gate, but you cannot use, for example, doping with CCZ, because then it will not be universal. So this kind of idea can be used. The only thing that I think, so in order to reproduce at least random unitaries, it's really to have this so one can have this group, but then has to have something that makes it universal. Otherwise, one will not converge to R. That's at least my kind of idea of the things. I hope it's so you need always something that complements it in a certain way.
Okay.
Because you need to build also the elements that are outside the group. Now, I don't know if you can always approximate even if you don't really are universal. This is a really interesting question in the sense that maybe you are not able to, I would say, asymptotically span the full unitary group, but you are able to span something that it's approximately the full unitary group, but still, I think it's it will be easier to consider something that make it universal. That's it, I will say. But it's really an interesting question to look out in general for any kind of group. That's
and maybe just a quick follow-up. Well, it's unrelated, but okay, Juni, you have a question?
Yes, I have a question, maybe a naive question. Actually, follow up the Gerald's first question during the talk. So you mentioned that it doesn't matter whether you put the T gates one each or on one layer. And I also heard that you mentioned this doping depth. The doping depth does it mean that number of T gates you doped into the circuit, or it is actually the depth of the circuits? Because if it doesn't matter that if you can dope the T gates together in one layer, why does it related to the depths?
No. So there was the circuit depth. Probably I was not completely. So the idea is that it's like you have a budget, let's say in terms of T gates that you have to insert. This is the minimal number. What I meant, so the order should be always the same. So the thing is this one. So you can have this Clifford, then now you can also put all the T gates here. Well, part of them. But then you will have problem in the convergence because you don't have them spreading around. That's kind of the point. But if you use the technique of having Clifford 1, Clifford 1, Clifford 1, it's basically kind of equivalent to the things of them spreading around. That's kind of the point of our idea. You can always do this. So you can always put all the T gates here. The only thing is that it will not be optimal in the sense that on average, you need more than basically having Clifford T, because these can be taught as free. These one are, you need to spread them in a good way. Of course, you can have 1, 2, 3, for example, but the things should be always a 1. But at the end, it will not really change the number of them, the order of the number of that you need. Still K-square is, that's kind of the thing. I hope it's clear. I don't know if I've been too clear, so that's why.
Okay, somehow I get more idea about this, the relation between the depth and the number of T.
So
gate.
when I mention depth, is basically the depth of the circuit.
Mhm.
What one can think about the T depth is more the budget that one has of these non-Clifford gates and wants to put in the circuits. That's kind of that's it.
Okay, thank you.